If you recall from the previous parts, we deployed 4 ceph nodes. We had 3 OSD nodes named OSD 103, 102, and 101, and we had a single monitor node. We looked at deploying ceph-fs, we looked at Rados block devices, and we ran some object benchmarks. We created pools using 3-way replication and a number of OSDs. In this part, we're going to expand a little bit on that. We're going to look at things like erasure coding. We're going to look at some more Bluestore commands, and then we're going to look at some of the more advanced command lines. So if we look at our system with the watch window, we can actually see that there's an existing cluster. So we want to purge that and get rid of it. So the commands to do that are here. ceph-deploy purge, and then you give the ceph node names. Then we purge the data from them, and then we finally do forget keys. So I've actually put this into a little script called del cluster. So we'll run that /del cluster. This will dismount all the OSDs. It'll get rid of all the authentication, and it's an entirely destructive command. What it may not do is clear some of the ceph-volume structures that are on the OSD disk, so we'll look at those, and we may have to go in and manually remove those using logical volume commands. So here's the system running. We'll just widen this out a little bit so you can really see what's going on here at the moment. It's saving the repos. You can see it's doing some yum remove commands, ceph release, ceph common, ceph Rados gateway, various ceph packages as well. When we do it this way, we're going to have to reinstall ceph as well. So we'll be going back out, doing the same thing as we did before. We go out and we do ceph-deploy and we install across the different nodes, which means it'll go out and it'll get the latest version of ceph as well. So something to keep an eye on is that by default we'll take the latest one. So if you're doing this with a little bit of time, you might get a slightly different version between that and the previous one. So just something to be aware of. What I did in this situation is parts 1, 2, and 3 were all recorded within a couple of days of each other, and there were no changes to ceph either in minor releases or major releases during this time. Alright, you can see now it's done most of the OSDs. It's on the last one here, OSD 103. It doesn't take too long to deploy the ceph data to purge that, and then the forget keys is nearly instantaneous. So you can just see it's really doing the same sort of thing. So we'll just give that another few moments. And now we're doing the purge data phase, and then finally we'll do the forget keys. Alright, so you can see the commands there. So that's all done. Alright, the final steps are all there as well, and there's the forget keys. Alright, so now that we've deleted that, we're going to have a look at the disks and see what's left on. Alright, let's have a look at OSD 101. And we'll do an LSBLK. And you can actually see the previous remnants that are left over there. So if we do something like LV display, this is a privileged command, so we'll sudo that. This is just a regular operating system, so let's scroll back a little bit and we can see there. So let me just repeat that command and we'll just pipe it into grep. So there's the volume group name, there's the logical volume path. So we can do sudo vg remove, and then we can give it the volume name, the volume group name, And yes, we do. And it's also going to remove the logical volume for us. So now if I do lsblk, you can actually see now SDA is clean. We need to do that on the other nodes. So we'll recreate the cluster using the similar commands that we did in part 1. So we do ceph-deploy commands, we install ceph on all the various nodes, and then we'll set up the manager services. And after that, then we'll recreate our OSDs. This time we're going to use the NVMe to actually offload some of the other Bluestore components. We haven't really spoke about them, but there's the write-ahead log and there's the database. So these can be co-located on the disk drive themselves, so they can be offloaded to faster media. So we're going to show that command where we offload it to faster media. So I've created a little script here which will make the cluster for us. So it's called Met Cluster, and you can see it has lines like ceph-deploy new on 100, the public network, and then we're going to install it on these nodes as well. We're also appending a string to ceph.conf, which allows us to delete pools. Before we did the inject args to do this, but we're going to put this into ceph-conf. Then we'll create the monitor. We'll push out the keys ready the admin to all these various nodes as well. Then we'll change the keyring on the mon node. We're then going to create the manager and set up dashboard and a few of those other things. So let's just run this command. And there it goes. So that'll take a few minutes to run. So in this case, we're going to create the OSDs directly on the OSD nodes themselves. So one of the first things we need to do is to do some key distribution. So I have a little tiny script here called copy keys, but let's run the first line. So we need to do this as a privileged user. So let's do that. Okay, so we'll just change to super user for this next one. Ceph demo. And then what we need to do is we need to copy the keyring for the Bootstrap OSD across. So let's do that in a small little loop. Again, using our default password, which we set up in part 1 of Ceph demo. All right. So now we can go back to the regular user and let's just set off the status command here. All right, that's now complete and we can see that the system is up and running. Of course, there's no OSDs have been created yet. So what I've done is I've created a little script here and I've used the convention that we'll have a one-to-one correspondence between the devices and the logical volumes. So for device SDA, I'm going to create a volume group called SDA volume group, and also there'll be a volume group for SDB. So what I do first of all is I remove any of the previous ones. Again, these are privileged commands. And then I create the new ones. So SDA volume group, and that'll be SDA, and then SDB volume group with /dev SDB. So we create the volume groups first, and then what I'll do is I'll just make sure that everything is created with the VG display and pipe that into grep. And then what I do is I create a logical volume, and this argument here is the number for maybe byte blocks. So effectively, this is going to work out as 20 gigs when you multiply this by 5,000. So again, it's going to be called SDA logical volume, which is a member of SDA volume group. The same for B. And then what I do is I take the NVMe device and I get rid of any previous partitions. There were 4 partitions here, and I recreate them. So I do sudo parted-a optimal, and then what I do is I make 4 partitions. So I break them up into different percentages. So this will create 4 NVMe partitions, and we'll use these for housing the WAL and DB components. So you can see this last command then, ceph-volume lva create --Bluestore. The data goes onto the volume groups, the logical volumes that we talked about earlier, but then I'm going to put the DB and the WAL on the NVMe device. So the WAL for the first one will go on to the first partition, P1. The WAL will go on to the second partition, and then I'll do the same thing for the second device, and then we'll use the third and the fourth partitions. So in a way, you would typically not necessarily break the NVMe up into 2 partitions. You might have a third level of hierarchy where you could use NVDIMM as well if you wanted. So you could have hard disk drive, then you could have flash media, and then you could use something like NVDIMM to get the speed going. All right, so now what we'll do is we've SSH'd onto OSD 101. So simply I'll cut and paste these commands just so that you can see them all running one at a time. All right, so you can see that it's removed the volume groups. Now what we want to do is create the next 2. So you can see now it's created the volume groups. Let's just have a look at those just to make sure everything is good. So you can see the volume group name is SDAVG and SDBVG. These other 2 here are the OS devices. So that all looks good. So next thing we're going to do is we're going to create the 2 logical volumes. So we'll just paste in those. So you can see logical volume SDA-LV and SDB-LV has been created. The next thing we want to do is we want to remove any partitions on the existing NVMe device. Okay, so that's all looking good. Now we want to create the new partitions here. And let's just have a look what we've got. So LSVLK, you can see the NVMe has been created and divided up into those 4 partitions. Then you can see the 2 logical volumes here, SDA and SDB. And again, this is the operating system disk, so everything looks good. All right, now that we've copied over the keys and prepared our devices, we'll create our first OSD on node OSD 101. We'll use that in this separate window here. So the command is running. You can actually follow to see what's going on here as well. There's the keyring that we talked about. Keeping an eye on that. There's one OSD coming up. Okay, LVM create successfully for SDA volume group / SDA LV, and there we go, correct. Let's do the second one. All right, there's our second OSD coming in. Okay, successfully created, and there we go. So we need to repeat that for the nodes OSD 102 and node OSD 103. So this time we're going to set up an erasure coded pool. Previously we set up a default replicator pool using 3-way replication. Erasure coding is more efficient in that it tends to use less capacity. It really makes more sense when you have more devices. So again, the rule will be to try and spread the data across drives on different servers. So we have 3 servers in our example, OSD 101, OSD 102, and OSD 103. So the rule set I'm going to create here is k = 2, m = 1. So K is really like the number of data disks, and M is the recovery one. So what will happen is when we write out some data, it could be that the data portion might be on OSD 101, the next data portion could be on OSD 103, and the recovery could be on OSD 102. But it'll always, by default, stripe across drives on different servers. So if we were to lose a server, we would not be able to recover until we introduce a new server. We could still get the data because we can recreate regardless, but we can't go into recovery mode because we need a minimum of 3 servers. So typically we would usually have a formula such as K equals, well, the number of servers should be equal to K plus M plus M. So what I mean by that is that ideally we'd like to have 4 servers. So K is 2, M is 1, and M is 1 again. So K equals, number of server equals K plus M, which will be 4. So ideally we want 4 servers. So here, while everything will work fine, we can't really tolerate another server failure. So this is the command here, ceph-OSD erasure code profile set. This is our rule here, EC profile 00. That's our rule set, and the parameters will be K equals 2, M equals 1. So now that we've created that, we can have a look at our rule. So we do ceph-OSD erasure code profile get, and then the profile name. So we can see here that the Crush device class is blank for the moment. We'll talk about that later on, but the device class could be something like SSD as opposed to HDD. The Crush failure domain is host, so effectively we're going to spread data across each of the individual hosts. We could, if we only have a single host, make our failure domain to be OSD. That way then it would do the replication across OSD drives in the same server. We can see the K equals 2, M equals 1, and we can see the various plugins, and we're using Reed Solomon Van der Mond for our recovery. So now we're going to create an erasure code pool, very similar to the way we did the replicated pool. We give it a PG number, then we tell it it's of type erasure, and then we give it the profile number. Okay, so the pool has now been created. You can see some activity going on above here. One pool, 256 placement groups. ceph-OSD ls. Oops. ceph-OSD ls pools. There's our erasure coded pool. If we use the command ceph-OSD pool ls detail, then we get a bit more information here. We can see EC pool 0, which is the name of the pool. The erasure size is 3, the minimum size is 3. So in this case, we need to have a minimum of 3 nodes to do it. The crush rule is the first crush rule. We'll look at the crush maps later on. We'll see the PG groups as well here. So that's some more detail on our EC pool. Let's check basic functionality with the Rados bench command. So hit enter here. All right. So just delving a little bit more behind the scenes, this may be difficult to see because there's quite a wide range of outputs. So I've made a small font to do this, but the command that we are looking at now is ceph placement group dump, and this can be very handy in fault finding. So there's quite a lot of data here. Let me scroll back up to the top and explain what this information really is. So we had 256 placement groups, so when we're dumping the placement groups, we'll have entries for each of these. So if we look at the top line here, we can see objects missing, primary, degraded, misplaced, unfound. So these are the kind of things that we need to look for to see if any of these placement groups are missing or degraded. So far everything's good. We can see in this case active plus clean. We can look at the date stamp. We can look at things here, which is the distribution of that particular placement group across an OSD. So what we're doing is let's look at this one, for example, 1.ff. So this is the hexadecimal format. This is the placement group number. You might recall that we said 256 placement groups. So FF in hex would correspond to the 0 to 255, so the last placement group. This number 1 here is the index for the pool. So we could have multiple pools. In our case, we've just created a single pool called EC pool 0, and that's given an index number of 1. So the number to the left of the dot refers to the pool number, and the number to the right refers to the placement group. So in the 255th placement group, we can see that that placement group is actually located on OSDs 2, OSD 1, and OSD 5. We also have a thing called acting. So if one of these OSDs had failed, another OSD might take its place. In this case, we have no failed OSDs, so the acting and the up are exactly the same. You'll also notice that the primary OSD is the first member. So here, just take one random 3, 1, 1, 4, 4. What this means is when you write, you do have to write them all. And again, in erasure coding, you're going to have to read from the data disk to recreate it. But in replication mode, the main difference is that when you write to all 3 of them. But when you're reading, you only read from the primary. So it's much faster from reading because you only have to read from one device, whereas with erasure coding, we have to do this from multiple ones as well. So there's other things like date stamps and scrubbing when all that took place as well. So you can see all the way down, we'll come along to all the different placement groups here. So, and then there's a summary down below here as well. So this is the placement group summary, primary placement groups, and this is the various OSDs. We might recall we created 6 of them as well, and these are the capacities of each of them as well. The available, of course, is much more depending on the replication that we used as well. So that's a little look behind the scenes of what's going on and how the placement groups are mapped to the various OSDs. So if we want to get a bit more detail, I can look at this last placement group here and do the command ceph-pg, the placement group number, which is 1.c5, and then I can query it. So let's press enter here. All right, we can see quite a bit of information. Let's scroll back up here. So Ceph is very good at giving you information, so it's usually very possible to get in behind the scenes and see what's going on. We won't dwell on all these various things, but you can see that there really is a wealth of information here, which allows you to go in and see what's going on. Again, this was the OSD that placement group was mapped to, so it used this case OSD2, OSD4, and OSD0 as well. You can see things like if it was scrubbing and all those that type of information as well. If I want to look at the PGs that are associated with a particular OSD, this could be useful really, I think, if you got into a situation where you are having problems with a number of PGs, you may be able to reconcile this to a particular OSD and then replace that OSD device. So if we look at the command, it's ceph-pg ls by OSD and then the OSD number. So we can see here that OSD0 is associated with placement group 1.ab, 1.ab, 1.af, and so on. It's not associated with 1.ac or 1.ae. So this is how we can reconcile which it's associated with. And you can see that OSD0 will appear in every one of these listings as well. If we're thinking we're having problems with a particular PG, we can try and repair it. So in this case, if we had a problem with PG 1.f2, I could issue this command. And then what will happen is it'll go off and it'll instruct that to repair it. You can see that the primary one for 1.f2, if I highlight this here, The primary OSD is OSD2, and you can see why it's saying instructing it on OSD2 to repair. That's where that comes from. If I'm interested in the mapping or the association of a placement group to OSDs, I can just do one at a time. I can do ceph-pg map and then the placement group number. So this tells me then, if I look at the map, it tells me the placement group 1F2 is actually mapped to OSD2, OSD0 and OSD5. If there are a number of PGs in a particular state, I can do a dump of those. So in this command, ceph-pg dump _ stuck, I can print out any of the stuck PGs. In this case, there aren't any, so everything's okay, and that's what I get printed. If I want to look at the contents of a pool, I can simply use the radars command, specify the pool number, and then an ls. So if I do this one, the listing that I can see is a number of files here, and these are remnants of a benchmark test that was ran earlier. So in this section we're going to have a little bit more about the Crushmap, and Crush is really the algorithm behind Ceph. So the first command we do is ceph OSD get Crushmap, and then we give it an output name, and basically this Crushmap that we're going to get is not human readable in this format. So we're going to call it the compiled Crushmap, and the system will go out and it'll grab that map for us. So if we just do an ls here, you can see it's down here as the compiled Crushmap. So the next thing we need to do is we need to invoke the Crush tool, and we need to decompile that Crushmap. And then we need to give it an output name, and we'll call it decompiled Crushmap. Let's just make that without a space. Alright, if we do ls now, we can see decompiled Crushmap. So let's have a look at that. Let's go into the editor, vi decompiled Crushmap. So we can see a number of things here. Device classes, HDDs. This is types is pretty important. This is really the way, really the buckets that Ceph will use. The default is to replicate the data across hosts. So when you're replicating data, it will take an OSD from one host, then it'll take an OSD from another host, and so on. It will make sure that the data is spread across OSDs that reside in different hosts. If we only had one host server and we really just wanted to get some experience with Ceph and we didn't really have many more systems, we could set the OSD replication to be of type OSD. That way we could do everything on a single node. So again, this is something you'd never do in production, but for learning a little bit about Ceph, it could be useful. So we can see the various OSDs here as well. It gives you things like the weight. We haven't really spoken about much. This corresponds to the capacity as well. And then there's various algorithms that you can use as well. So we're using straw2 in this case as well. So let's just go down a little bit more. And we can see the EC pool rule set that we created. By default, you'll always have the replicated rule, so you don't need to go in and modify the Crushmap or create any rule sets if you want to stick with replicated pools. But if you want to use other pools with different device classes, maybe such as SSDs or NVMe's, you want to use a different replication type, then you could go in to do this. So if I wanted to modify this system so that we could replicate across OSDs instead of across a single server, I could come along here. I could simply change this to say type is OSD. So that way I wouldn't need to have 3 different OSDs or 3 different servers to do the replication. So this is what it looks like. We can then edit any of these files that we want. And when we've got everything done, then what we can do is we can take the Crush tool again. And what we could do is we could recompile the file. Let's say if we had made some changes here, we would want to recompile it here. And then we would need to give it an output file name. So we could call it modified Crushmap. And so now what's happened is we've created the new Crushmap with our changes, and then finally what we need to do is do ceph-OSD set Crushmap, inject it, and then this one, modified Crushmap. So in our cases we didn't actually make any changes to the Crushmap, but that's how you would do it. Alright, let's clear that screen and let's go back and look at the OSDs in a little bit more detail. So here's the 6 OSDs that we created. You can see the nodes they belong to. This is the weight, which corresponds to the capacity of each of those OSDs as well. If we do something like ceph-OSD df tree, then we get a little bit more information about the usage of the various OSDs as well. If I do ceph-OSD stat to get some statistics, we can see basically that everything's good on that front. If I do ceph-df on its own, this is similar to above, except it's not broken down to the same level of granularity as well. If I want to perform a scrub, I can do ceph-OSD scrub and then give it the OSD number. So now what's happening is it's going out scrubbing OSD. I can also do the deep scrub command as well if I wanted to do that. One thing that's also very useful is that we can reconcile OSDs to particular file names. So if we have a look at our pool, we can see various benchmarks files there, which we talked about earlier. So if we want to see how an object is associated with a particular OSD, we use the command ceph-OSD map, pool name, and then the file name. So when we do that, it tells us that this object here is associated with that particular placement group, and then these are the OSDs that that placement group is associated with. When investigating performance issues with Ceph, it could be the case that one particular OSD could be responding very slowly, but yet it still hasn't failed. So that could really compromise the performance of the cluster to some extent. So we can look at individual OSD performances by using the ceph-tel command. So in this case, what we're going to do is a quick benchmark on OSD 0. So this will run for a few seconds and it will tell you how many bytes that it was able to write within that particular period and give you an idea of IOPS. Let's just compare that one with, say, OSD 5. So in this case, you can see that the values are fairly similar. IOPS a little bit slower here, block size, and so on. So this is a way you could tell if one of the OSDs was starting to fail. To get a bit more information about the OSDs themselves, we can issue the command ceph-OSD metadata. So you can actually see each of the various OSDs are here. Again, we could grep this to filter which ones we want. But there's OSD4, and OSD3, and so on. Just having a quick look at them, you can actually see things like the ID. So we can see that this is on the node with an ID of 102. In other words, OSD102. These are the port numbers here. You can look at the back-end interface. This is where you might want to use a separate NIC for replication purposes. And then you can see various things here as well. You may recall on this one, we set the DB component to be up on an NVMe device as well. And there's the partition paths. The WAL type was also NVMe. So quite a bit of information here, the version of ceph. So again, this is a very useful command to find. If we need to stop an OSD and take it out of the system, well then we need to do a command like ceph-OSD out, and then the OSD number, let's say OSD number 5, and then it's marked out. Now we need to go to the OSD 103 node, and we need to do sudo system control stop ceph-OSD at 5. After we've done that, we can go back to the monitor node. We can do ceph-OSD purge 5, and then we need to put in dash dash yes dash I dash really dash mean it. All right. So now if we do ceph-OSD tree, oops, small typo there, OSD tree, and again OSD tree, we can see that OSD 5 is now gone. And basically what's been happening is there's some rebalancing that's gone on. Now the system is all back clean again as well with the missing OSD. If you want to get some more information about OSDs, we can go on to the OSD node itself. In this case, I've moved on to OSD 101. And then I can get information by specifying the particular OSD. So here I want to look at the configuration for OSD 0. So I use this command. And we can see there's a wealth of information here. So when you're looking at this, you most likely want to filter it with grep or some tool like that to extract the various information that you're actually interested in. So again, I think there's probably well over 1,000 entries here as well that you can look at. You can also do other commands here, such as perf schema. And then this gives me quite a bit of information as well on the performance side of things. So again, this is something that you can experiment with.